The traditional spin statistics theorem stands as a pillar of mathematical physics, relying on a massive superstructure of continuous Lorentz symmetry, microcausality, and Whiteman axioms. This field operator algebra raises a foundational question: whether the link between spin and statistics is a theorem of continuum operator algebra, or if that math is a higher-level encoding of a more primitive geometric fact. The research proposes that the boson-fermion distinction derives from local geometry without needing commutation relations or continuum fields. We start within a pristine 3D network of interconnected tetrahedra, the S-grid. Here, exchanging identical excitations manifests as a physical geometric braid of their paths. Spin is the twist periodicity required for an orbit to return to full identity, a topological feature of the excitation itself. Within this framework, the positive and negative phases of particle exchange emerge directly from the logic of Braid twist closure. In a discrete universe, statistics is a mandatory geometric corollary of local Braid mechanics. We define a discrete spatial substrate, the tetrahedral S-grid, and a temporal sequence, the T-grid. A particle world line embeds the T-grid into the S-grid. It moves via a local propagation operator, H, coupling spatial steps with angular twists, generating a spiraling corkscrew world line. These excitations are orientation-bearing orbits. Their closure properties provide the geometric data necessary to define spin. We must now identify the mathematical requirements for such an orbit to achieve full identity closure under repeated actions of the propagator. The lattice supports two closure classes. In the fermionic class, returning to full spatial and orientational identity requires two full cycles, a strict 4π twist periodicity. Conversely, a bosonic orbit achieves full trivialization in both position and orientation after only a single 2π cycle. Full closure for this class occurs already at 2π twist periodicity. We define spin in this architecture as this minimal twist periodicity requirement. Spin is thus a geometric feature of the corkscrew orbit, rather than a label imported from continuous symmetry. Moving to two particle interactions, we consider a pair of identical corkscrew world lines. We bypass the continuum approach of symbolic label permutations. Instead, we represent exchange as a local geometric deformation, a physical braid of the two paths. Defined as theta b, this discrete exchange element causes the two world lines to wind around each other exactly once before continuing in their exchanged positions. Geometrically, this move advances the mutual linking number of the pair. A single physical exchange corresponds to an advance of exactly 1 unit of mutual twist. This topological braid provides the mechanism necessary to evaluate the statistical phase. The outcome depends on whether the exchange braid element is trivial or non-trivial within the closure class of the pair. For a bosonic 2π pair, one braid fulfills a complete closure period, leaving the state identical with a +1 phase. Conversely, a fermionic 4π pair requires two braids for closure. A single braid covers only half period, resolving in an inverted state. Here, theta b behaves as a non-trivial square root of identity. Two full exchanges would be necessary to return the pair to its original state. Because the state is mathematically opposed to the original after one exchange, it yields a phase of -1. This completes the theorem. The 4π class mandates fermionic statistics, and the 2π class mandates bosonic statistics, driven by braid topology. The derivation yields a clear result. Same braid, different statistics. The lattice, the propagator, and the physical motion of the braid remain constant. The statistical phase is forced by the internal closure periodicity of the single particle. This model operates with a strict structural economy, using no independently tunable parameters. In continuum QFT, commutation relations are an external postulate. In this lattice, they are a geometric necessity. As the discrete S-grid blurs into continuous quantum fields, the analytical machinery of QFT reveals itself as an emergent encoding of the lattice logic. Operator algebra does not create spin statistics. It repackages a more primitive discrete geometric fact. Spin is the timing of closure, either immediate or delayed, under local propagation. The foundation of matter and force is a corollary of local braid geometry in a discrete universe.